Moving away from the purely inertial and barometric simulation capabilities, we will start to look at some of the architectures being employed for sensor fusion. Current military vehicles have a tendency to employ multi-sensor navigation systems utilizing discrete boxes with separate hardware interfaces and specific or proprietary aspects to each device. The electrical interfaces of these devices may include RS-232, 422, 1553, Ethernet, discrete I/O, or synchronization pulses. The overarching navigation processor must then accept, interpret, and process each distinct sensor input. Progress is readily being made towards sensor fusion-based architectures, with commercial applications making great strides, with military and defense beginning to make headway as well. In a generic sensor fusion architecture, as pictured, multiple sensors are physically connected via Ethernet. Each sensor and type has logic to output according to the established standard. The navigation processor performing the data fusion will have sensor configurations defined via user input. The key implication of this architecture is that despite the architecture change, as always in navigation systems, timing is key. To maintain timing and synchronization, high-quality frequency references and time synchronization messages are employed. Real sensors, this keeps time and rate outputs from drifting. In simulation, one of the boxes on the left is a simulator, outputting multiple types. Errors are also simulated, so having the time and frequency references allows for modeling the actual sensor effects. If following open source standards, as we will discuss in a bit, as long as the device adheres to the standard, sensors are interchangeable. The SimAuto and SimSensor products are currently available and allow users to simulate various aspects of sensor fusion algorithms. SimSensor offers integration of MEMS sensors, be it magnetometers, gyros, accelerometers, barometric sensors, or digital compasses. As needed with all products, noise injection is available for error budget testing. Support for multiple sensor streams is available with multiple transmissions. SimAuto offers users a solution for testing GNSS with dead reckoning sensors. This allows for comprehensive system testing and facilitates rapid turnaround. System uses analog voltages to simulate heading and heading rate sensor outputs, uses digital I/O for wheel speed sensors and direction of travel. As the commercial world is progressing down this path, the military and defense industry is also beginning to incorporate these capabilities and architectures into modernized systems. To that end, Spirent is partnered with government and industry to develop an open Ethernet interface for simulation of non-GNSS sensors. Comparatively, the available sensors and test interfaces Spirent supports currently is shown here. The OEI will enable realistic sensor modeling via Ethernet connectivity, allowing for control of error inputs, maintaining low latency communications, facilitating precise timing, and use of a flexible protocol definition to provide users flexibility in device selection. Here's a notional interconnection diagram of simulation capability when the OEI is implemented. The goal is to convert existing Ethernet and other sensor outputs to the OEI standard, and finally implement the OEI time synchronization messages. The OEI implementation will provide benefits to end users, developers, and integrators. There will be a flexibility to limit the number of discrete units to reduce the overall swap of the system. There's the removal of risk of being forced into a specific sensor OEM and any rigid associated architecture. Vendor competition will increase and allow for market entry for smaller, less established firms. Overall integration will be simplified and will allow for a quicker fielding of new technology and a shorter turnaround on system upgrades.